Hello student, how are you doing? This video is the continuation of the video regarding surface integrals. On the previous video, we evaluate surface integral or integrand was a scalar value function, such as if you had a surface and you had a function f of x, y, z, and you try to evaluate that surface, that function has to be continuous function on a smooth surface. That surface has to be a smooth, continuous, and the z must become function of x and y for all the x's, for all the x value and the y value in the region which the surface is building on. Therefore, the surface integral was equal to your integrand was a scalar value function x, y, but z was a function of x and y, and the surface area was partial derivative of x squared plus partial derivative of y squared plus 1 dA. In here I should have put ds in here, but the minute you replace ds with the surface area, that s must be changed to the area of the region. An example was that if you did have a surface like z equal to x squared plus y squared, you know the trace on the, if the y become constant, the trace on x and z is a parabola, and if x become constant, the trace on the zy is a parabola, but if the z is a constant, the trace xy is going to become a circle or an ellipse. Therefore, this is elliptical paraboloid, but that's only my surface, and my z value is fluctuating between 1 and a 0. Therefore, if z is 0, you have a point, and if z is 1, you have a unit circle, and that's what is going to be the ugly picture, and that's what is going to be an elliptical paraboloid, and that should become elliptical paraboloid right here. Okay, then I want to give you a function of f of x, y, z, and that function is x squared plus y squared. Okay, I need my, remember this is my surface, and the function I'm evaluating is x squared plus y squared over the surface, but I need the surface area. Your surface area is the square root of partial derivative of x squared plus partial derivative of y squared plus 1 dA. Then you sum this one up, you get a surface area. But in here, you have to have x value, you have to have a y value, you have to have a z value. Therefore, you have to write your function right here explicitly, and maybe I'll call it the w x, y, z, and make this one x squared plus y squared minus z. Somebody said, well, should I bring x squared y squared to the other side and make the z a positive? Since here you're going to square them, no matter which one become negative, and you square them, it become a positive. Therefore, what you have right here, you're going to write the surface of region, and here you have x squared plus y squared, and instead of ds, you're going to write partial with respect to x, which is 2x squared. Partial with respect to y is 2y squared. Partial with respect to z is negative 1 squared dA. You know this is 4x squared plus 4y squared plus 1. And if I factor the 4, you have x squared plus y squared plus 1. Since when I'm talking about the region, I need to go back and look at the top, from the top of my graph, and see what is the projection of that top of the surface over the xy plane, and that's nothing except a circle with a radius of 1. Therefore, my region is a circular region. Therefore, I'm gonna make a polar coordinate with a theta from 0 to 2 pi, your radius 0 to 1, and this become r squared, and this one it become 4r squared plus 1, and r d theta. Let me write this one for you to be able to see it. Therefore, you have 0 to 2 pi and 0 to 1, x squared plus y squared, which instead of that one we wrote r squared, and the square root of 4r squared plus 1 r d theta. And in here you have to find this become r cubed, and in here you have to do some kind of a substitution to be able to integrate it. I'll leave this one up for you to go ahead and evaluate it. Tonight in this short video we're going to talk about what happens if your integrand excuse me, become a vector field. Okay, when you talk about vector field, and sometimes maybe you can make a real life example that you do have a surface, and inside that surface you're gonna carry some kind of a fluid, but some kind of a vector field, or you're gonna move some substance. There are some substances going to be moved by using a vector field, but what you need to do in order to do those, this surface have to be very smooth. Therefore, here whenever we're talking about surface integrals of a vector field, we always going to talk about two-sided surfaces, or sometimes they call the two-sided surfaces an orientable surface. Somebody said, what is a two-sided surface? A sphere is a two-sided surfaces. Either the flow gonna go out or the flow gonna go in. Ellipse is gonna be two-sided surfaces. Either the flux go out or the flux go in. A plane is two-sided surfaces. Either go out or either comes in. What do I mean that going out and going in means? In order for two-sided surfaces orientable and become smooth means at every given point in here around the surface, at every given point in here, I'm not talking about the boundary point. Boundary point could be exempt, but I'm talking about those. For every one of these points, you must have a normal vector. And the normal vector must have pretty much same direction. Somebody said, what do you mean by same direction? Means if you are walking over the surface and if your head is up, at any given point you go, your head must be up. Means you cannot have, there are some surfaces, let me see if I can make a surface, they are tilted, and then when you go in here, your head is up, surfaces, and these are not two-sided surfaces. Maybe when you go from the top, the unit vector faces up. When you go underneath of it, the unit vector goes down. In here, we're talking about two-sided surfaces must be orientable and it must be smooth. Other than that, we're not going to deal with surfaces which they are not orientable. Then, if you do have a surface, we're going to talk about a flux integral, and the flux integral is when you do have a vector field, you have a vector field, and that vector field is moving in a direction, and in here you have a path, and there is an object on that path, and that vector field moves that object according to the path the object is located on, which we use a unit tangent vector to determine the movement of the object. But at the same time, when you have a tangent vector, you have a normal vector. That normal vector could go out or it could come in. Therefore, the projection of the vector field times t, that causes a force, and that force along a path, or that force along a surface. Remember, that's a lowercase, that's uppercase. These are a line integral, but this is on a surface. This is called circulation, and also in here you can call it circulation, but also you can call it work. Also, same formula you're using for work. But if you take the projection of that vector field over a normal vector for here, then that tangent vector and that normal vector, that tangent vectors and that normal vectors, this tangent vector and this normal vector. And if you do have a normal vector at every given point, and find the cumulative sum of all the dot product of vector field with the normal vector, and if you sum it up over the surface, that's called flux. Flux can go out, flux can come in. That's all. There is a difference between them is a sign. If it's in the outside of the z, therefore you have to have a positive z value. If it's opposite side, the negative side of the z, that becomes a negative. If it goes in the direction of x, positive x or negative x, or in a direction of y, positive y or a negative y. Therefore, in and out, right or left, they all depend on it only changes by a positive to a negative or a negative to a positive. Therefore, we have to consider a couple of things when we're talking about that flux. Sometimes you have that vector fields right here, which these are all parallel, and you see that vector field and that unit tangent vector, they're consistent with each other. They're exactly opposite each other. Or maybe there are some tangent vector that is in the same direction as the vector field. Therefore, in here you have to say a few things. If you have a surface and if you have a vector field, and if you do have a unit vector and if there's a unit normal vector to the surface, and if this angle is theta, then f dotted with a n is going to become, you have to consider one of them x-axis, the other one have to become a y-axis, and then you have to say this is nothing except the magnitude of the f, magnitude of the n, cosine of theta. And you know the unit normal vector, the magnitude is 1, therefore if it's between 0 and 90 degrees, that's what it becomes, and you have seen this before. But if you do have a surface and you have your normal vector and your vector field are exactly in the same direction, then the f dotted with the n, these are in the same direction, is exactly the magnitude of the f. But somebody said, what happened if the vector field, if the normal vector is that way and the vector field goes that way? Therefore, you have to say f dotted with the n is exactly the negative of the magnitude of the f. But someone said, what happened if you have a vector field and a normal vector, and this angle between them is 90 degrees? What is the cosine of 90? 0. Therefore, f dotted with the n becomes 0. Means you're not going to have no flux whatsoever. Then, remember previous problem when we talk about surface integral of a vector field right now? We're going to write all the formulas. This is your surface, f dotted with n ds. In here, okay, what is your normal vector? Normal vector comes from a surface. And if you remember, we always said the gradient of the function is always normal to the level curve. That's one thing. Therefore, if it's a scalar value function, you can consider its gradient as a normal vector, but gradient the magnitude is not 1. Therefore, you divide it by its magnitude, and that's become a unit normal. And somebody said, what happens if it's flux out? Therefore, you have partial derivative of x, partial derivative of y. But this has to become a plus. Therefore, if your function is z equal to x squared y, you cannot move the z to the other side because you're fluxing out. You have to bring those to this side. Therefore, that's become negative, and that's become a negative, and that's become a positive. But if you want flux in, you gotta take the become in means negative side of the axis, the z goes to the other side, and the f of x become positive, and partial with respect to x and partial with respect to y become a positive. Therefore, here that's something that you have to be very careful if they're talking about flux in and flux out. And that's how it is. Therefore, if you do need a unit normal vector, if it's a scalar value function, you can use gradient. But somebody said, what happens if it's the parameterized surface, and your x is a function of u and a v, I, and your y is a function of u and a v, j, and your z is a function of u and a v, k. In here, you have rate of change in the direction of u axis. You have rate of change in the direction of v axis. Means r of u, I'm assuming, is a vector. If this was become r of x, a unit vector could be a unit vector along the x-axis. If this one was r of y, it could become a unit vector along the y-axis. And when you cross these two together, that cross of these together, it become orthogonal to both, which was your z-axis. Therefore, if it is parameterized, you can take the partial derivative with respect to u and v, cross it, and divide it by its magnitude. And when you divide this one by its magnitude, that gets you a unit normal vector. And you do know when you cross two vectors, that become area of a parallelogram. Therefore, if you cross these two And if you sum up all the area of a parallelogram over the surface of R of U and R of V and the magnitude of it over the S, that becomes the area. That's the surface area. Then, for finding the flux across a surface using a vector field, you have two formulas. F dotted with the N ds. If it's a parametrized surface, you write vector field dotted with R of U crosses with R of V over the magnitude of U, magnitude of R of U and V times ds. But your ds, which is the area, is going to be the magnitude of R of U crosses R of V dA, and that's become a region. That one and that one is gone. Therefore, if you do have a vector field over a surface, you need the region that the surface is built upon it, and you need a vector field dotted with the cross product of RU and RV times the area of a region. But somebody said, what happened if I have a surface integral, a flux over a smooth surface, and I do not have parameterized surface? You have to write F dotted with the gradient of the function over the magnitude of it. A surface area is the partial derivative of x squared and partial derivative of y squared plus 1 dA. That's the area of a region. But somebody said, what is this? This is your z, which is a function of x and a y. If they ask you flux out, you want to make sure that z is positive, and you write z minus f of xy equal to some function wxyz, and the gradient of that w now, let me call this one a w, is negative partial derivative of x, negative partial derivative of y, and 1. But what is the magnitude of the gradient? Negative partial derivative of x squared, which is become a positive, negative partial derivative of y squared, which is become positive, plus 1. If you look at the magnitude of the gradient, is exactly the what? It becomes the surface area, or the integrand of a surface area, and these two will cancel out because this is a gradient and this one cancel out. Then what happened? This will become a region. That's the vector field, but in here you dot it with a gradient dA. You gotta know these two problems whenever you solve any surface integral with integrand become a vector field. Let's do an example. We do have a surface z, and that surface z is 4 minus x squared minus y squared. In here, if your z becomes 0, you have a circle with a radius of 2. If z becomes 4, you have a point. Therefore, this is elliptical paraboloid faces down. I want to know if I do have some vector field, which that vector field is a function of x, y, z, and that's x, y, and z. What is the flux? And remember, maybe this elliptical paraboloid has a whole bunch of points in here like a strainer, and there is a fluid coming through it, and I want to know what is the cumulative sum of all the flux when there is a hole here, the fluid goes that way. But maybe the normal vector is this way. Maybe the fluid goes that way, but the normal vector becomes that one. Therefore, on every one of them, we take f dotted to the n and we sum it up across the surface. That surface must become a smooth surface. It must become two-sided surface. And as a matter of fact, elliptical paraboloid is one of those oriented surfaces because it goes out or in. It is two-sided. Then if I want to find the surface integral, I need f dotted with the n ds. Is this parametrized surface? No. I don't need partial derivative with respect to u and v, but I need a gradient if I and I need flux out. Therefore, my z has to be positive. The x come to other side, x squared become positive, y go to other side become positive, by the 4 become negative. And I call this one g of x, y, z. The gradient of g is 2x, 2y, and a 1. And the magnitude of the gradient is 4x squared plus 4y, 2x squared plus 2y squared plus 1. Therefore, I need a region here. The region means z must be 0. The projection of that surface over the xy plane. And I have a vector field which is x, y, and a z, dotted with a normal vector. I need gradient over the magnitude of the gradient, but because it's not parameterized, I have to put my surface partial derivative of x squared plus partial derivative of y squared plus 1 squared dA, and I see that one and that one cancel. All I need is the gradient, and the gradient is 2x, 2y, and 1 dA. Good. Because the projection of the region, because my region is a circle, I'm going to use polar coordinate right here. But somebody said this is only x and y. Yes, if you remember a few minutes ago, I wrote down that your z must be a function of x and y. Your z must be a function of x and y. For every xy, you must have a z value. And that's come from your surface, because surface gives you a relation between x and y and z. Therefore, I go right here and I said this is a polar coordinate from 0 to 2 pi, or it's from 0 to 2, and I'm going to dot it. X times 2x, 2x squared, y times y, 2y squared. But instead of z, you have to put 4 minus x squared minus y squared. And when I dot it with the 1, you get 4 minus x squared minus the y squared dA. 2x squared minus x squared is x squared. 2y squared minus y squared is y squared plus a 4. This is nothing except r squared plus a 4. Therefore, your dA is r dr d theta. And if you go ahead and finish the problem, you have from 0 to 2 pi, 0 to 2, you have r cubed 16 over 2 is 8. That's making it 12. And when I integrate theta from 0 to 2 pi, I'm talking about d theta. That becomes 12 times 2 theta, and that becomes 2 pi, 24 pi. Therefore, that always giving me that how much this one gonna take care of it, the total flux is gonna be out. Therefore, this is whenever you have a scalar value function, but there are certain occasions. Let's do another maybe examples. Let's consider in your house is raining. The rain is coming down exactly in the direction of the z, is not a slant, and the x component is 0, the y component is 0, the z is -1, and this is nothing except your force field, or that's a vector field. But the roof has the shape of z equal to 4 minus a 2x minus a y, and it f dotted with the gradient dA. My f is 0, 0, -1. My gradient is coming down. My z must be negative. Therefore, I'm going to write 2x plus a y minus a z minus a 4 equal to, nope, I brought the z to this side. This is a negative, this is a negative, and therefore it's positive. Therefore, the gradient respect to x is a -2, respect to y is a -1, respect to z is a -1. And that becomes 0 plus 0 plus 1. Then the dot product of f with the gradient is 1. Then I have a region 1 dA. Therefore, the surface area is exactly become the total flux in a downward direction across the surface and I'm going to have to say across the surface, but that surface is going to cover, that plane is going to cover many houses. But I'm going to say, let part of your house become first occupant. How do you find the area? First occupant z is 0, x and y are positive. Therefore, if I make my x 0, your y is 4. That becomes dy. And if I solve for my x, my 2x is equal to 4 minus y, and my x is 2 minus half a y. And my x goes from 0 to 2 minus half a y, and that's not a big problem that you cannot solve. Therefore, that's another thing that you can use in order to solve the surface integral when you do have a vector field. Okay.